So, when you hear Unreal Engine's Niagara, you're probably thinking about sparks, right? Maybe some cool explosions. And hey, you're not wrong, but that's really just scratching the surface. See, Niagara has grown into something way bigger. We're talking about a complete data driven simulation platform that is totally changing the game for real time graphics.
But to really get why Niagara is such a big deal, we need to take a step back and look at a fundamental problem, one that pretty much every real-time artist and developer has to deal with.
This right here, this is the million-dollar question. It's what keeps developers up at night. It's this constant nerve-wracking tightrope walk between building a gorgeous, immersive world and making sure the game actually runs well enough for people to play it. Okay, so you've got these two sides, right? In one corner, you have visual fidelity. This is all about those dense, stunning effects that just suck you right into the game world. But in the other corner, you have peak performance. That's your silky smooth frame rate, the thing that makes the gameplay actually feel responsive. In these two, they are always fighting. It's this constant tug of war, and for years, artists have been caught in the middle, having to make some really tough compromises. So how do we get out of that bind? Well, this is where Niagara's really brilliant architecture comes into play. It gives artists this amazing toolkit to handle that challenge, giving them a structured way to build even the most mind-bendingly complex effects. At the very heart of Niagara is something called the execution stack. Think of it like a recipe. The system is the overall dish you're making. Inside that dish, you've got emitters. Those are your individual ingredients. And each of those ingredients is controlled by modules, which are basically these specific cooking instructions, like dice, sauté, or simmer. And this table, it shows you exactly how that recipe gets made, frame by frame. Everything flows from the top down. It starts at the system level for big global rules. Think wind that affects everything. Then it goes to the emitter to figure out how many particles to create. After that, it updates what every single particle is doing, its speed, its color. And finally, it tells the renderer how to actually draw it all on your screen.
Let's make this real with a simple smoke effect. First, you set up your system. Then, in the emitter, you tell it to spawn particles at a constant rate, not just in one burst. At the particle spawn stage, you give each new puff of smoke a random size and lifespan, so it looks natural. And finally, in particle update, you add a little force to make it rise up. See? It's a super clear step-by-step process. So you've done it. You made the perfect effect. It looks incredible. But now, what happens when you need a whole lot of them? I'm talking about a battlefield with hundreds of explosions, or a dense forest with thousands of leaves falling all at once. The old way of just spawning a new effect for every single one, well, it just doesn't work. You are going to hit a performance wall, and you're going to hit it hard and fast.
And this is the exact problem that Niagara's newest features were designed to completely obliterate. And we're not talking about small tweaks here. These are major shifts in how Unreal Engine can even think about handling VFX on a massive scale. You don't have to take my word for it. Daniel Pearson from Epic Games said it perfectly. Just spawning a ton of actors for every little thing is a huge performance killer. The engine has to keep track of every single one, and that overhead just builds up like crazy. So, solution number one is the stateless or lightweight emitter. Just look at this comparison. The old school stateful emitter costs a good chunk of CPU power for every single instance. But a stateless one? It costs next to nothing. It's incredibly light on memory, and while it's a bit simpler, the performance you gain is massive. The takeaway is simple. Use the big, stateful emitters for your unique hero effects, and then use these lightweight, stateless ones for all the thousands of ambient details that make a world feel alive. And the second game changer? Niagara Data Channels. Let me give you that chef analogy again, because it's perfect. Instead of hiring a new chef for every single grain of rice, you just give one master chef a huge list of orders. That's exactly what data channels do. Your game just sends a little piece of data, like the exact location of a bullet impact, into the channel. And then one single powerful Niagara system is just listening for those orders and spawning particles wherever they're needed. It's genius. And check it out. This is what it looks like right in the editor. It's not some hidden, complicated thing. It's just a simple asset you can create, just like a material or a blueprint. You just go to FX, then Advanced, and bam, Niagara Data Channel. This makes this incredibly powerful system easy for anyone on the team to use. So here's how all the pieces fit together. You've got three main parts. First, the data channel asset itself. That defines what information you're sending. Second, a Niagara system that's set up to listen to that channel. And third, a blueprint, which is your game logic that actually writes the event data into the channel. These three things work together perfectly to slash the number of actors you have in your world.
All right, so with performance issues being crushed by lightweight emitters and data channels, a whole new question pops up. What can we actually create with all this new power? And the answer is leading us to a level of physical realism we once thought was totally impossible for real time.
This leads us right to the substrate material framework. Now, this is a huge shift in how we even think about materials. Artists are no longer just fiddling with abstract sliders like opacity or specular. Now, they're defining materials based on their actual physical properties, treating them like little slabs of matter. This comparison really shows the jump. In the old system, if you wanted to make smoke thicker, you basically just made it less see-through. It would just kind of fade out. But with substrate's mean free path, which is a real physical value, thicker smoke actually absorbs more light and gets darker, just like it would in the real world. This is what lets you get that realistic self-shadowing and that truly volumetric feel. And that right there is the key. This is the whole point. Our visual effects are no longer just flat images layered on top of the game. Now they are physically baked into the world's lighting. They absorb light, they cast real shadows, they feel grounded in a way that just skyrockets the sense of immersion.
So that leaves us with this final thought. Technologies like data channels and substrate, they're not just about making things look a little bit prettier. They are about systematically tearing down the technical walls that have held back artists for decades. And as those walls start to crumble, the real question becomes, what new worlds, what incredible new experiences are artists going to dream up next?